Okay, so here's the next exercise. It does look a little bit more complicated, but don't worry, this is quite simple as well. We see that these three here are connected to the ground. Okay, so I guess the first thing that we can do will be to mark them as 0 volts in this node here, 0 volts in this node here, and 0 volts in this node here. And we can separate them as well. We don't really need these wires here. Okay, now something else. Let's see. So there are three currents going through. So there's one current coming in this direction, there is one current coming in this direction, and there's another one going this direction, and this one will be here at point V1, and this node here will be equal to the node here V1. Okay, next let's see. So here we have at the top here we have another I value, and there's another one coming through here. So there's another node here. We'll simply call this node here V, and this current I will go through this node here, and it will still be equal to I. Okay, now it will go through this node, and in this node there are other two currents. There's another current coming in, and I guess we'll call this one I1, and this one will be I2 because this current is coming out. Alright, so we got two currents coming inside the node and one current coming out. Let's see, is there anything else that we can do to simplify it? I don't think so. I think this is everything we need to do. Okay, so the first step will be to find V1, because if we don't know the value of V1, then we can't really find out the value of the current here. So what we do first will be this. So there are two currents coming through in point V1. So then let's see, there will be 0 volts and there will be V1. So 0 minus V1 divided by 2R. Okay, and then there's another one here plus Vs minus V1, and then we again divide by 2R, and that will give us 0. Alright, now we can just simplify because they have the same number here. We get rid of the 2R, so then we get minus V1 plus Vs minus V1, that will be equal to 0. Okay, and then therefore minus 2V1 plus Vs, that will be equal to 0. Now what we need to do is to move Vs the other side, so it'll be 2V1 equal with minus Vs. Okay, and then therefore let's write it as the final answer. So therefore V1, we'll get rid of the negatives, it's left with only 2V1 will be equal with Vs divided by 2, and we need to remember this value here. Alright, now let's keep going. So we separate it here so we don't mix it up. Okay, so we know the V1. Now we can find the value of I, and let's see, but we also need to know the value of V. V is still an unknown, so the way we can do it is to apply Kirchhoff's law here, and we can do 0 minus V1 over R equal to V1 minus V, V1 minus V over R again. So we can get rid of the resistances, then therefore minus V1 will be equal with V1 minus V, and then therefore minus 2V1 will be equal with minus V, and we can write this where this is going. Therefore let's do the blue. Therefore V will be equal with 2V1. Alright, so now we know the value of V as well. So we know the value of V1 when we know the value of V. Because we know the value of V, we can find V2. And V2, no, V out, sorry, not V2, V out will be equal with the current 2, I2. So I2 here is got two currents coming in, I1 and I, so I2 will be equal with I1 plus I. Alright, Therefore, so we can do like I2 will be equal to V minus V out over R. So V minus V out over R equal with I1 here will be equal to 0 minus V over R. 0 minus V over R. And then here for this I will be V1 minus V over R. So plus V1 minus V over R. Okay, we can get rid of the R values. So then therefore we get V minus V out, and that will be equal to minus V plus V1 minus V. Alright, we can simplify, so then we get V minus V out equal with minus 2V plus V1. Alright, we can move it then this V2 to the, no, let's move this V to the other side. So then therefore minus V out will be equal with minus 3V plus V1. Okay, let's switch signs as well. So then V out will be equal with 3V minus V1. And for the last step is because these values aren't really good values, we would rather use the Vs value instead. We can switch them. So then therefore V out will be equal with V here, it will be equal to 2V, so it will be 2 times 3, so that would be 6V1 minus, and this V1 is equal with Vs over 2, so that will be Vs over 2. Again, we still have the V1 here, so we need to do it one more time. So V out is equal with 6 Vs over 2 minus Vs over 2. And then therefore V out will be equal with 5 Vs over 2, and that will be equal with 2.5 Vs. Alright, and that will be the final answer. We can either put in fraction form 5 Vs over 2, or you can say 2.5 multiplied by Vs, and that will still give you the V out. Alright, again, another simple exercise. And again, it's very important for you to know to put a notation for every node. For example, if you ignore this V node and we didn't put a notation to it, and we just calculated the V1 here, then that will make it very complicated, because you get to this point and you may think like, do you ignore the top current coming through here, or do you just notate a different one and which direction the current goes, you know? So again, it's very important for complicated circuits like this one, before working through it, to notate it. We know every node noted with the value, and every current, write every current as well. Anyway, thanks for watching, and I'll see you in the next exercise. Okay, so before this exercise we did many exercises that got the op amplifiers going in the same direction, from left to right. Yes, but what if you do an exercise that got, yes, it's got two op amplifiers, but they are in opposite directions? This one will go in this side and this one will go in this side, and not only that they're in different directions, but they feed each other as well, because this one will go in here and it go to the negative pin, while this output here will come and eventually get to this negative pin as well. Okay, it took me a while to figure out how to do it, and this is kind of the best way I've came out with. So, because this is actually quite hard. It's not hard to calculate, it's more like hard to comprehend, because, you know, it's very, very different from what we did before. So first of all, no current going through here, and again no current going through here, and because this is the negative, no, this is the positive pin, so V2 will be equal to the value here. So this one will be V2 here, V1 will be equal to the V1 here. Now, what may be a bit confused is this amplifier here, because it's dead at the middle, and we don't know the voltage of it. What I realized that the voltage doesn't really matter here, because there's no resistance through here, so there's no voltage lost when the output comes out of it. So we can say this one will be V out 2, V out 2. Okay, So you may say like, well, as is possible, is it actually equal to the V out minus, no, to the V1 minus V out 2 divided by R1? And the answer is yes. I don't know, as I say, like, these are maybe the most confused. But remember, if there's no resistance going through here, that means that the voltage stays exactly the same. So if you find this voltage V out 2 here, even though you calculate only with Kirchhoff's law through the currents, then you can theoretically actually find the output straight away. But we are interested in this voltage output, not in this one. Okay, and we can name this one V out 1 as well, because the output here will split. Some of the current will go to the V out here, and some of the current will go to the V out here. And V out 1, it's exactly equal with V out, so we can say they are equal to each other. Anyway, okay, now another interesting thing is the direction. Okay, how do I explain this? So I think the direction will be something like this. First I thought that the direction will be something like this, it will go this way like that, but no, it won't. It will actually go from the 0 value all the way to the voltage output. So let me mark it with another color. It will go something like this. Okay, let me go on the top, and there you go. So that will be the value of I. It will go from the 0 point and it will end up at the voltage output point, and it will go through this wire like this. Okay, I can't really draw that, but that's fine. Now I thought, what about this here? Is there a current going through here? And I realized that there probably isn't, because there's no voltage or anything like that. But I guess we'll mark it anyway as an I2, and there's definitely a current coming through here, and that one will be I3. Okay, so there's the big current here, I, coming through the resistor R2, R1, R1, R2 on the top here till it gets to V out. So that's the main one that we are going to use. I'm not 100% about I1, I2 and I3. Again, this is like the hardest one that I came across, because it, like, I don't know, it like flips it upside down. It makes you like, it makes it so much more different when you do so. Alright, so let's start with the first half here, because we can say that this I here will go through here and it will stop at the node VO2. Okay, sorry, my brother walked in. Anyway, so yeah, there is this current here, and we can say that the current I will come in this node, and the same current I will come out of this node as well. So we can apply Kirchhoff's here to find the value of V out 2 and the value of V out 1. Now, okay, next, so we will start, but this one is added too far as well. Sorry, and as I said, I'm not very good at this one. So yeah, we can do that, but we still don't know the values of V1 and V2. So first we need to find the values of V1 and also the value of V2. Okay, so now that we got the plan, so let's find the value of V1 first. V out 2. So 0 minus V1, 0 minus V1 over R2 will be equal with V1 minus V out 2, V1 minus V out 2 divided by R1. Therefore, we can simplify it as, if we can multiply by R1, so we can simplify it as minus R1 over R2 times V1. That will be equal with V1 minus V out 2, V out 2. Okay, then we can simplify, and we can take V out 2 out, so then there will be V out 2 equal with V1 times 1 plus R1 over R2. Alright, so this one will be the first one. So now we need to do it for this side here with V2. V out 2 minus V2 minus R1 will be equal with, let's see here, V2 minus V out 1 over R2. Okay, therefore R2 over R1 multiplied by R2 divided by V out 1, no, divided by V out 2 minus V2, that will be equal with V2 minus V out. Okay, so V out 1 or V out, depending which one you want to go do, because they are basically the same. Now let's think about it. So, or we can write it as this. We can calculate V out now. So we need to isolate V out from here. So then therefore V out will be equal with V2 minus R2 over R1 times V out 2 plus R2 over R1 times V2. Therefore V out will be equal with V2 1 plus R2 over R1 minus R2 over R1 times R2 plus R1 over R2 multiplied by V1. We can get rid of the R2s from here. Okay, and then therefore V out will be equal with V2 bracket 1 plus R2 over R1 minus V1 1 plus R2 over R1, and then therefore the final answer will be V out will be equal with 1 plus R2 over R1 multiplied by V2 minus V1. Okay, it is a bit of a messy answer, but to be honest, it's also a little bit of a messy circuit, because I mean, I don't know what kind of purpose would this serve, because amplifiers are really easy to control. You just need to put the resistance values. But if you have something like this, like the opposite of them combined together, going in different directions and feeding each other off, then that will make it a lot harder. I'm not sure what you can use this one for. I just saw it and I thought about showing it to you as well, how I figure out how to do it and how I did it. And again, it's based on this here, on the V2, and basically on the current I going through here, because we calculate the first half here and then we calculate the second half here, and we get this answer here. Probably it would be more of a clean answer if you either knew the voltages or if you knew the resistances. But anyway, so this is the method to solve a circuit like this one, and I'll see you next time. Okay, now on this exercise, you may say, well, there isn't really, from the first view, there isn't really anything complicated. We do have two OP-amplifiers, and yeah, we can determine easily where the current go through and what type of the amplifiers they are. Now, the interesting part I want to show you is now we don't have a normal V out. Now we have a resistor load for V out. And you may say, well, why did you do this? And the answer is because mostly that's how a voltage output will actually look like. It will be a resistor, and you calculate the voltage inside that resistor because you connected in parallel. You know, usually, like in the previous examples, see if I can grab a few of them, we just simply had a V out here, and the same for this one here as well, just a simple V out. But in more like practical circuits, you can just have like an empty wire and have the voltage output through there. I mean, yeah, you can have that, but sometimes you want to have the voltage output going through a resistor. Now, what we do? Well, let's start with the basic steps, and you'll see why this is a bit more different than a normal Vout that we calculate. So there is no current going through here, and there is no current going through here. This is the positive pin, so we can call this one V1, meaning that this one will be equal with V1. Now this one, it's 0 volts at the positive pin, so there will be 0 volts here, meaning there will be 0 volts through here as well. Alright, there's no current going through here, so then there is a current I coming to the two resistors, and it's on the current I coming something like this. Okay. Alright, now the interesting part of this exercise is that the RL, the way we calculate the voltage output, is by taking these two nodes here. This node will be VA, and this node will be VB. And the way you calculate Vout, I'll write it in blue so you can see, in case you ever need to, is we simply do Vout equal with VA minus VB, and that's how we calculate through the voltage Vout through RL, because you need to remember that these two are different voltages. Even though they are connected in parallel, it's not really connected in parallel with only one component. It's connected in parallel with two different voltages. One voltage, the output of this op-amplifier will end up here, and the output of this op-amplifier will end up here. If they were both of them connected through one wire and it was connected to the resistor, then yes. But because it's not, then that's where we calculate it. Okay. Now, it's also important to show that V1 here, the V1, it's also equal with, it's also here, V1, at the positive, yeah? Meaning that this V in and this V1, they are the same one. So V1 is equal with V in, okay? So we know with that to replace it. Alright, now let's start with what is simple, and that would be the top side, because the top side, it's a simple inverting, is it inverting? Yeah, it's inverting amplifier. Now, so let's write here, top side, that would be 0 minus V1, so 0 minus V1 over R. This is a current, and Kirchhoff's law, so this will be the second current, will be equal with V1 minus VA over 3R. We can get rid of the R's, and then we'll get something along the lines of minus V1 over, no, minus V1 equal with V1 minus VA over 3. Now we multiply this one by the value of 3, and then therefore we get minus 3 V1 equal with V1 minus VA. Therefore minus VA, it's equal with minus 4 V1, and therefore VA, it's equal with 4 V1. However, we know that V1 is equal with V in from this, so we can also write it as, and it's indicated, write it as, let's see, VA, it's equal with 4 V in. Okay, now we need to go to the next one. So we did the top side, the easy side. Now we go to a bit more complicated side, which is the bot side, the downside. So down side. Okay, let's start with the first current going through. So there's a node here, therefore we can apply the same method. So V1 minus 0, V1 minus 0 divided by R is equal with 0 minus VB divided by 4R. 0 minus VB divided by 4R. Okay, we get rid of the R's, and then therefore we get V1 equal with minus VB over 4, and we'll multiply this one by 4, so therefore we get 4V1 equal with minus VB. Now we know the value of V1 as V in, so we can rewrite it as, therefore, minus VB will be equal with 4 V in. Yeah, sorry about this. That. Anyway, so then V minus VB is equal with 4 V in, therefore VB will be equal with minus 4 V in. Alright, now what we need to do is we need to apply this formula here. V out is equal with VA minus VB. In my notes I did it in a different way. It is a bit more complicated, a bit more long-winded, but I decided to like short it out a little bit. I hope you saw what the calculations that I did, but it's nothing special. It's exactly the same calculation that we applied up here, but this time we applied with the values here. Okay. Now V out will be equal with VA minus VB. We know that VA is equal with 4, so therefore V out is equal with 4 V in, and we know that VB is minus 4 minus bracket minus V in. Okay, and then wait, sorry, 4 V in, there you go. Okay, therefore V out is equal with minus that's 8, oh, it to be a positive, to be 8 V in. Okay, and what does it mean if it's a positive 8 V in? Well, that means that the current flow will be from VA down to VB, so it will be in this direction, if I'm not wrong. Okay, now let me check. So VA down with the bigger one. Yeah, that's the correct answer, to be from point VA to point VB, the current flow. Now let's write it with blue, and you can, because you may ask like, well Alex, how did you know that this is the formula VA minus VB? Well, this is a basic format to like find the voltage between 2 points, which will be in point here in the RL. But also you may ask, well, how do you know which one to put in front of which? How did you know that you are supposed to put VA in minus VB instead of putting VB minus VA? Because what if you put it the other way around? And I'll show you what happens, because this happens quite often. You are not 100% sure which voltage will be higher than the other voltage. So if you do like V out equal with this time VB minus VA, then we replace them, we'll get V out is equal with minus 4 V in, and then it will be minus 4 V in, and therefore V out will be equal with minus 8 V in. So it will give us the same answer, but this time it will be a negative value. And what does that mean? It means it goes in the opposite direction. So instead of going, so how do you explain this? You are not supposed to have negative values. It's ideal to have positive values, because this will make it a bit more confusing. Because if this was a positive value, if VB was higher than VA, and if this one was positive, the minus 8 volts, if it was 8 volts, then the current will flow in the opposite direction. But because it's a negative one, you know that this is not the case, that actually it still flows in the same direction, because again it's a negative it's a negative value. Okay, I'm not sure how well I explained that to you, but as I said, the idea is that if it's a positive value, when doing it's not division, it's the minus, when taking away VA from VB, that means that VA has more voltage, meaning that the current will go from VA to VB. If the answer is negative and you do VB minus VA, it doesn't mean that VB is higher and it goes to VA. It means the opposite. It means that VB is lower, meaning that it will still be the same direction from VA to VB. What we need to do, you need to be careful on this sign, okay? And if you're not sure of the answer, you can do it again like I just did here. You can either check it with VA minus VB, or you can check with VB minus VA to get the correct answer. Anyway, okay, so that was it really. Another simple exercise, but I just want to show you how to calculate if you need to find the voltage inside the resistor instead of just the voltage out of a wire. Okay, thanks for watching, and I'll see you in the next one. Okay, now you may look at this one, you may say, well, this is a bit strange. Why? Well, we have this arrow here and we have a resistor here. Well, this resistor is different from these resistors. And why is that? Well, it's because these ones are normal resistors, and this component here, it's something called a potentiometer. I don't know if you heard of them before or if you learned about them before, but I can do a quick sketch for you. So basically what the potentiometer looks like in diagram, it's something like this. And what they do is that you can change the resistance. For example, if this side's 100k and this side's at the middle, then there will be, let me get blue, then there will be 50k on the top side and 50k on the bottom side. And how you connect this, usually it's like you connect one side to ground and the other side to the circuit. So the current flow will be something like this, and what the current says, it says the 50k volts, so it will see a resistor with 50k. Okay, now the idea of the potentiometer is that if you use the exact same potentiometer, but what we can do is, let me draw it again. Okay, and here's the arrow, here's the dot, it's 100k. Oh no, sorry, I drew it wrong. Sorry, let's say it's something like this. Okay, and then the total is 100k. Okay, but this time it's higher, and we can say that now on the top side it's like 10k, and then the bottom side is 90k. Okay, again we connect the downside to the ground, and the current will only follow this resistor here, which will be the 10k. And it's exactly the same potentiometer, but you just move the values up and down like this. Okay, and the current will follow one of them. Now you may say like, well, if you follow only this value here, why does it have to end? Well, that's how potentiometer works. For example, if I make this one higher, no, if I make the top one lower, like 10k, then the rest of it will be 90k, because it will be 100k minus 10k, and then it gives me 90k, and so on. You can't really get rid of that one, and you can use this side. You don't always have to connect to the ground. You can use it by connecting to another circuit, and then they'll both meet at the same point. Okay, something like this. And let's say you have a higher current going through, no, a lower current going through it, and you have a higher current going through it, like let's say this one is I1, and let's say this one is I2, and then you get like an I total coming out. Okay, and it's a way to like control the currents with a potentiometer. This example is here because you will actually use potentiometers quite often with OP-amplifiers. And you may say, well, why would I use a potentiometer with an OP-amplifier? As I said, I don't know when you are watching this video, but most probably is when you went to the laboratory and build an OP-amplifier, the teacher or tutor, this is not teachers now, it's tutors now, will say, well, Alex, not really Alex, well, we have to place a potentiometer in here and a fixed resistor in here, and they'll tell you to connect an oscillator at the output and the ground, and to tell them what's the voltage. And you have the potentiometer, and you will increase and decrease the resistance, and then you'll get different frequency with a different peak for the voltage. And that will teach you that you can control the reference point with the potentiometer, and depending on the resistance you will get a new output value, a new gain. Okay, the idea is that you're using potentiometers quite often with OP-amplifiers, and I want to show you how you calculate with a potentiometer. So let's say this one is perfectly at the middle, at the center. Okay, so we can just draw something like, oh no, this is not the blue one, so we can just draw something like this. Okay, and we can imagine there are two resistors in here. Okay, and this resistor here is 20k, and this resistor here is 20k. Again, it's like in perfect center. Now also we have the positive pin here. Let me write this out with red. We also have a ground here, so we can say this one is connected to ground, and we can also say that this one is connected to ground. So we don't really need these two wires here, just start simplifying the circuit. Alright, next will be, because these are the positive pin, then this one will be 0 volts. Okay, then this point here will also be 0 volts because they are equal to each other, these two pins. Wait, oh no, sorry, this pin here is 0 volts. Sorry, I got carried away. Forget about this. Remember, there is a junction there, but forget about that one. Okay, next. So let's see, there are currents as well, and there's one current coming through here like this, but you also remember there's a source in here as well, and I should have put like 4 volts in the source because this one is 4V. Alright, so there's a junction here, and let's call this junction here V1. Alright, then we will call the current coming through here that goes to V out as I. So we will call this current here as I as well. Okay, that will be I. We will call the current coming, let me mark it with blue. We'll call this current here I1, and we'll call the current coming out of here I2. Okay, now we can see that I1 will split in two. Alright, so then so if I1 was split in two, we can say that I1 is equal with I plus I2, but we want to find the value I here, so therefore I will be equal with I2 minus I1. Okay, so that should be good enough. Yeah, so move this on here, that will become a negative as well, because we move it to this side, and then move this I here to this side, that will become negative. Okay, so then what we do next is we actually start calculating. So this I here, it will be a negative. We don't really use negative currents. This is a new one. I guess it's because for the way it's split, because these two currents don't meet at this point and come out at that point, they come down and split in two, and that's why. But anyway, so then I will be V1 minus 0, so V1 minus 0 divided by the 20k ohms. Alright, and that will be equal with, and I1 will be equal with, no, it's I2 actually. I2 will be V1 minus 0 over 20k ohms minus, and then I1, this one will be 4 minus V1, so 4 minus V1 over 20k ohms. Okay, you can already realize that I did so just because I would be able to cancel them. But remember, you can do it with the potentiometer at any value. The only difference will be if I move this one higher. Let's say if this one is 10k, then this one becomes 30k, and you can do it with any variables you want, really. Okay, now we can rewrite it as V1 minus V1 will be equal with V1 minus 4 minus V1. Alright, so then this V1 will cancel with this V1, so then therefore minus V1 will be equal with minus 4, therefore V1 will be equal with 4. Alright, is it correct actually? So positive, negative, yeah, it does seem correct. Okay, Now let's go to the next one. So we got the value for V1, which is 4. Next, now we can calculate this I here by using this I here. So the I here, that will be V1 minus 0 over 20k ohms equal with 0 minus V out over 30k. 0 minus V out over 30k ohms. Alright. So then we can replace the value of V1. No, actually let's make this on the common factor. So we multiply this one by 3, we multiply this one by 2. Therefore we get 3V1 over 60k ohms equal with minus 2 V out over 60k ohms. Okay, and we can cancel those k's. Therefore we get 3V1 equal with minus 2 V out. Alright, now we replace the V1 with this value here, which is 4. So then therefore 3 times 4, that will be equal with minus 2 V out. Okay, and therefore that will be 12 equal with minus 2 V out. Okay, and then the answer would be, therefore V out will be equal with minus 6 V. Alright, let's keep going. So we did one of them with one switch. I was thinking, like, what if we do it multiple switches? And let's say we close this switch S2 that I'll mark with red. Let's say we close this one and then the rest of them will stay open. Well, how do you calculate then? Well, if this one is closed and the rest is open, then there will be no current going through the 3 of them, and there's also no current going through here or here. And V in as the positive pin, so then let me mark with black. So then V in will be here, and to be at the negative one, which will be at this point here, V in, at this point here, V in, this point here, V in, and this point here, V in. Alright, now V in will go from this point here, and you'll see that it splits into directions. The current will go either down here, and it will also go up here. Okay, so we can see that this V in, it will be equal with V in at this point here as well. Alright, okay, then let's do Kirchhoff's current law. So let's start with the V in going down. We can see that it goes, V in will go V in minus 0. No, it will go 0 minus V in. It will go upwards like that. So to be 0 minus V in, 0 minus V in divided by 500 plus 500 plus 1k. So that would be 500 plus 500 plus 1k, and that will be equal to the other half, which will be the other I, and that will be 2k, no, that will be V in minus V out, V in minus V out divided by 2k, divided by 2k. Right, we can rewrite this one as minus V in over 2k, wait, minus, no, it shouldn't be 2, yeah, it is minus 2k, and that will be equal with V in minus V out over 2k. We simplify, we can cut the 2k, so then we get minus V in equal with V in minus V out, therefore minus 2V in, because we move it to the other side, will be equal with minus V out, and then therefore we get rid of the negative, so V out will be equal with 2V in, and we can write it as AV is equal with V out over V in, and that will be equal to 2, and that 2 will be the gain. So whatever voltage is coming through here, when it comes out to be double. Oh, sorry, I forgot, you didn't see the last one. AV is equal to V out over V in, and that will be equal with 2, and that's the gain. Okay, I should like remind myself to move this one a bit higher when we do it. But this was kind of like too simple, you know. So let's go, and what if we close 2 switches? So let's say that this one is again opened, and this time we'll do the problem with the color blue, so there's no confusion. And let's say that we close the switch S4 and we close the switch S1, then there will be no current going through this one or this one. This point here will be V in, this point here will be V in as well, and then there will be nothing to those two nodes, and that will make three currents. It will make the current I coming from 0 to V in, another current I coming from V in to V in, so there'll be another I, and another I coming from V in to V out. Alright, now actually this V in will be equal with V out, so we can write this one instead of V in, we can write it as V out, because there's no resistance in the way, so yeah, we can just write it as V out. Alright, now let's see, so let's start with the one here. So 0 minus V in divided by 500, so 0 minus V in divided by 500, then there will be V in to V out, and that one will be V in equal with V in minus V out divided by 500 plus 1k plus 2k, 500 plus 1k plus 2k. Okay, and therefore minus V in over 500 will be equal with V in minus V out over 3.5k. Alright, now we can multiply this one by 7, and then therefore minus 7 V in will be equal with V in minus V out, because we will make these two the same value. Alright, here will be 3.5k, and this one will be 3.5k, and we will simply simplify it, so we get rid of the two of them, and then we get minus 7 V in equal with V in minus V out. Alright, now we move this V in to the other side, so then therefore minus 8 V in will be equal with minus V out. We get rid of the negative signs, so then therefore V out will be simply equal with 8 V in. Alright, and that will be the answer, that will be the gain. So AV is equal with V out over V in, and that's equal with 8, and that's the gain. Okay, so there will be just a simple gain of 8. So when we close switch 2, the gain becomes 2, so as we calculate here. So whatever we put in V in, it will come out twice as big as V out. But if we close switch 1 and switch 4, then the gain will become 8, and then whatever V in comes in, it will come out as 8 times bigger. Now you can do some really interesting circuit with something like this, especially if you combine this with logic gates. Instead of using switches, you use logic gates, and depending on one certain condition, and then you can change the gain of the voltage V out. Again, I just want to show to you that you can do some interesting things when applying switches to an op amplifier. And also I think I will apply it next year as well, like a lot of switches with logic gates in op amplifiers. But anyway, so that was the exercise, and hopefully you find it useful, and I'll see you in the next exercise. Now this one's another simple one, because instead of a voltage source we have a current source here, meaning that the actually let's start simply. Okay, so no current going through here, no current going through here, and we know that this one would be V1 and this one would be V1 as well, because that's the positive pin. But we also know that it's a current source, meaning that the I from here to the pin, that will be 1 milliamp, and meaning that that 1 milliamp will also go through here, so that will be also equal with 1 milliamp. Okay, all right, so that will make it already simpler now. But before we can do this, we need to find V1, which V1 is here as well, and it is connected to the same output. meaning this is a differentiator operation amplifier. I think it's differentiation, I don't think it's comparator. But anyway, so let's draw the currents. So a current is coming through here, a current is coming through here as well from the bus downside. So, and they will combine here at the V out. Alright, and we can, yeah, so let's start with the bottom side. I guess we can notate them as well. So we can call this one I, we can call this one I1, and we can call this one I2 if you really wish to. Anyway, so let's get started. So V1 is also down here, so this one will also be V1. So the current here will be 0 minus V1 over 40k, so that'll be 0 minus V1 over 40k equal with V1 minus V out, because it's going to V out, so that'll be V1 minus V out over 60k. Alright, now we multiply them, so multiply this one by 3 and we multiply this one by 2, therefore minus V1 over let's see, that'll be 12k, yeah, 12k will be equal with, no, that'll be also 3V1, there you go, be equal with 2V1 minus 2V out over 120k, and we can simplify these ones, we can get rid of that. So then therefore it will be minus 3V in equal with 2V1 minus 2V out, and we'll move the V1 to the other side as a negative. So then therefore we'll get minus V1 and 5V1 equal with minus 2V out. Therefore we get 5V1 equal with 2V out, and therefore we can simplify, so V out, no, we need to find V in, yeah, so V in, V1, sorry, not V in, V1 will be equal with 2 divided by 5 V out. Alright, so we found V1 that we'll use here. Now we can use it there, so I will be equal with V1 minus V out, V1 minus V out over 20k ohms. 20k ohms. Okay, therefore 1 milliamp will be equal with V1 minus V out over 20k ohms, and then therefore 20 will be equal with V1 minus V out, because we do 20k ohms multiplied by 1 milliamp and we get 20. Okay, therefore 20 is equal with, now we replace V1 with this value here, 2 over 5 V out minus V out, and we can either multiply by 5 or do V out, we do this equation, but let's multiply by 5, that's 5 times 5. Okay, therefore it will give us 100 equal with 2V out minus 5V out. Alright, therefore, okay, that will be 100 equal with minus 3V out. Alright, then therefore V out will be equal with 100 divided by 3, and we reverse the sign, so this one will become a positive, this one will become a negative, and that will be equal with minus 33.333 recurring 3. Alright, and that would be the answer. So that would be the gain in this amplifier. It will be minus 33.3333, which seems fine, to be honest. Okay, so you saw how to calculate, and again, we could have done it the other way around. We can have used V out and then replace the V1, but then we wouldn't know the value for V out, really, we will find out the value for V1. Anyway, this is another simple exercise. I just wanted to share it to you because we got a current source instead of a voltage source, and thanks for watching again. Next one will be the last exercise for today. Okay, this one is the last exercise for today. and this one is a little bit more complicated. Again, it's not complicated to solve it, to put the to calculate it. It's complicated to understand it. Let's start with the basics with what we know. We know there's no current going through here, there's no current going through here, no current going through here, no current going through here, okay? And we know this node here is 0 volts, and it's at the positive, meaning that this node here will also be 0 volts. We know that this one is 0 volts as well, meaning that this one here will also be 0 volts. So we got those two. Alright, what else do we know? Well, we know there will be a different voltage at this point here and at this point here, because it will be the output from this op-amplifier will be here. So there'll be V prime here, and the same voltage output from this op-amplifier will also be here. So this one will be V prime here as well. Okay, and we need this V prime because we need to find the current. Alright, so that, and I'll mark with blue the current. So I'll pick the blue one. There's no current going through here, meaning that from V positive it will go all the way down to V prime in a straight line, so that will be 1I. There's no current split in here, it just in series. But in this one here, also let me mark it, because V is here at the top, so this one will be V here as well, and this one will be V here as well. It will be the same voltage but split in two. Now here there's a junction here, so this will be the current I, but it will split into directions. It will go down here as I1, and it will also go this direction as I2, okay? And that I2, it's also the I2 used here, because it's at the junction here. The problem now is that this is what we need the V prime. We need to V prime because we need to find I1, so we can actually calculate the current I2 that's coming through, and then being able to solve the problem. Okay, you may notice that this problem is a bit more complicated, and also you may notice that unlike the other problem, let me see if I still have it here, just a second. It should be somewhere around here. If not, we can just like, oh, there it is. Okay, unlike this one where the amplifier's direction is going in this direction, in this one the amplifier directions are coming in the opposite direction, going in the other way around. Okay, alright, I just want to like show this distinction. But again, remember that one of the amplifiers still fits the other one, like in this example here. But again, you don't follow these two because they are very, very different between them. There's a very big difference between them. Now, okay, let's see. So first things first, we need to find this V prime, because we don't know this V prime, we wouldn't be able to use it here. Now, how do we find V prime? Well, as I said, there is the current I here and it's in series. So we can calculate the current I going at this node, and then the current I also coming out of this node. Okay, then we can write it as V minus 0, so V minus 0 divided by R1 over R1 will be equal with 0 minus V prime, 0 minus V prime divided by R1 again. Okay, we can simplify it and get rid of the R1, and then we'll get V equal with, V equal with minus V prime, and then therefore V prime is equal with minus V. Alright, so we got a value for V prime, which is this one here. Now we can calculate it here, and again it's very, very simple when you actually calculate it. The hard part is to figure out where the currents go through and what nodes you need to look out for. Okay, so we can write the formula for this one. I is coming inside this node, and then I2 and I1 is coming out, so we can write it as I, it's equal with I1 plus I2. Alright, and what we need to find is this value here, I2. Okay, so then we can rewrite it as I minus I2 is equal with minus I plus I1. Alright, so let's start with I2. So let's write this one, what should we call it? Should we call it like V1? Yeah, let's call it V1. Okay, so then minus 0 minus V1, 0 minus V1 over, oh wait, there's nothing here actually. Okay, so if there's nothing here, that means that I2 won't use V1 here, it will use instead the V out. Okay, 0 minus V out, and then it will be divided by R2. R2. Alright, simple enough. Sorry about that, I forgot. If there is no resistance there, of course, the voltage won't apply. I can still use this one. Yeah. Okay, let's keep going. That will be equal with minus the value of I, and I will be V minus 0 divided by R1. So V minus 0 divided by R1 plus the value of I, and I will be 0 minus V prime divided by R. 0 minus V prime divided by R. Alright, we can't really simplify it, so let's rewrite it a little bit. So that will be V out over R2 equal with minus V over R1 plus, no, actually to be a minus V prime over R. Alright, now what can we do next? I guess we can get rid of all of the R's in the fraction form. But do we really need to do that? No, not really, because we just want the V out. So what we'll do is we'll multiply by R2. So multiply by R2 to get rid of the R2 from here. So then we'll get something like this. We get V out, it's equal with minus V times R2 over R1 minus V prime times R2 over R. Okay, let's see. So then we can also rewrite it as V out will be equal with R2 times bracket V over R1 minus V prime over R. Alright, let's see, and we can actually simplify it even further because we know that V prime is equal with minus V. So then therefore V out is equal with R2 times V over R1 plus V over R. And we can simplify it even further away by saying that therefore V out will be equal with R2 times V close brackets multiplied by open brackets 1 over R1 plus R. Can I do that actually? No, let's just leave it like this by 1 1. There you go. Right, let me rewrite it. Okay, therefore V out will be equal with R2 times V times 1 over R1 plus 1 over R. Alright, and that would be the final answer because yeah, it does make sense. So yeah, don't forget about the currents. Be careful with the currents because for some reason I didn't calculate it with the minus 2 I2 equal with minus I plus I calculated I it's equal with I1 plus I2, and that's obviously wrong. This is the correct answer to it. Is it really that wrong? Let me check. I mean, like, if I used I and that would be equal with I1 plus I2, then this one will still be V out, wouldn't it? Yeah, so it shouldn't make that much of a difference. Let me go through this again. So there's a negative, that will make a positive, that will become a negative, that will stay a negative, okay? Then that says negative, okay? Multiply by R2, so negative, and then Oh, it's one of the mistakes. This one was supposed to be a minus as well in the bracket. There you go. There's the mistake. Okay, so that's a minus and a minus. And why did I, oh, this one became a positive because of the v became a minus. Okay, but this one still stayed a negative. All right, so then, okay, so I'll rewrite it again. Sorry about me rewriting. Sometimes, as I said, sometimes I just miss one of the signs. For example, I missed this sign here, in here, and that's why when I went down I got the wrong answer. The correct answer is not this, the correct, because we follow this one, so then theoretically the correct answer will be, therefore, V out will be equal with R2 times V, but it will be equal, multiplied by, and it will be 1 over R minus 1 over R1. There you go. And that is actually the correct answer. Okay. Yeah. No, I was wondering, like, because I got my notes here, and I was wondering why I got the positive here and not the negative. And I was thinking maybe I solved it wrong in the notes, but no, actually I solved it correctly, because again, it doesn't really make much of a difference if we move the currents, because V out will still be inside the equation, to be unknown in the equation. But I guess I like to move the currents, so it makes a little bit more sense in this way. And also the calculation was a little shorter, I guess. Anyway, so that was the last example. Thank you for watching. And yeah, probably this video will be shorter than the other ones, and that's because the next videos will be about capacitors, no, not capacitors, about filters. So we are going to use capacitors and AC sources, so we are going to move forward towards that type of amplifiers. Okay. I hope you understand what I did here and how I calculated, and thank you again for watching. See you next time. Bye.